In this video, I want to take a look at exam revision for probability generating functions. So what I'm going to do here for this video today is take a look at a number of exam style questions for probability generating functions. And as you can see here, this covers the following topics. So we have understanding and using probability generating functions. We have probability generating functions for standard distributions. We have the mean and variance of a distribution, as well as the sums of independent random variables. So as always, pause the video, have a look at the questions as they appear, and then double check that your solution matches what we get on the screen. That gives us everything that we need here then for our introduction. Let's get started with question 1. Let's get started then with question 1 here. So for question 1, we have the random variable x here, which has the following probability generating function here. So I've got g of x in terms of t. So let me just highlight this here. Now, for the first part of this question, then part A, it just asks us to find the value of k here. So how do we find the value of k then for part A? So to do this here, we need to use the following property here for probability generating functions. So we're going to use here, so we're going to use g of x when t equals 1 is equal to 1. Okay. So in that case then, what do we get here? Well, I get k plus 1 over 5. So we then times this by 1 plus 1 squared plus 1 cubed. So 1 plus 1 squared plus 1 cubed. And this here, as this property states then, is all equal to 1. Okay. So let's simplify the left-hand side here. So we get k plus, so what I've got here then inside the bracket is 1 plus 1 plus 1, so that's 3. 1 over 5 times 3, and we get 3 over 5 there. Okay. And that is equal to 1. So in that case then, nice and easy here. We just want the value of k. All I need to do here then is subtract 3 over 5 off both sides. So k is equal to 1 minus 3 over 5, giving us 2 over 5 there. Okay. And there we have it. So nice and easy. That gives us the solution there to part A. Now for part B then. So for part B here, it asks us to find the probability that our random variable x here is equal to 1. So the probability x is equal to 1. How do we do this here? Well, the first thing that I do then is I just rewrite this PGF here. Obviously, we just need to replace k then with 2 over 5. And what I'd do then is I'd also just expand this bracket here. So altogether then, what we have here is g of x in terms of t. And that is equal then to k here, which is 2 over 5. So k is 2 over 5 plus 1 over 5t plus 1 over 5t squared plus 1 over 5t cubed. So let me just write that down in full then. So 1 over 5t, 1 over 5t squared, and then 1 over 5t cubed. Okay. Now, if we want the probability that x equals 1, what I'm looking for here is the term. So it'll just be a single term here because it's just an exact probability. So I'm looking for the term here where the power of t is this number here, which in this case is 1. So that would correspond to this term here, right? Because the power of t here, we don't write it, but that is a 1. So that's t to the power of 1 there. So in that case then, this probability here is the respective then coefficient, which in this case is 1 over 5 there. So our solution then to part B here is 1 over 5. Okay, so that's part B done. And then finally here for part C, it now asks us to find the probability that the random variable x here is strictly less than 3. So x is less than 3 here. So just as we saw then for part B, obviously this time now it will be terms because there will be multiple terms here for this probability. So what I'm looking for now is any term here where the power of t is less than this number here. Okay, notice this is a strict inequality here. So what terms would that correspond to? Well, it won't be this term here because the power is 3. We want strictly less than 3, so it won't be this one here, but it will be everything else because this power is 2. This power here is 1. And we don't actually write the t, but this is t to the power of 0. So it's this term here, which we've already highlighted, and then finally this term here. Okay, so what I need then is the respective coefficients for each of these three terms here. So I've got 2 over 5 plus 1 over 5 plus 1 over 5 here, like so. Add these together here, and then what we get is 4 over 5 there. Okay, so there we have it. So that gives us the solution there to question 1. Let's now take a look then at question 2 here. So what do we have for question 2? Well, we have the discrete and variable x here, which has the following distribution. So x follows a binomial distribution with parameters then of n equals 3 and p is equal to 0.2. So for the first part of this question, then part A here, it just asks us to state the probability generating function of the discrete and variable x here. So x follows a binomial distribution with parameters of n equals 3 and p is equal to 0.2. So to find the PGF here, the probability generating function, well, this is just for a standard distribution here, right? So in that case then, to find the PGF, we simply need to use our formula book here and obviously just apply that then to this distribution here and these parameters. So in that case then, if x follows a binomial distribution with parameters of n and p, the PGF here, I'll just give the result given in the formula book. So g of x in terms of t, this is equal then to 1 minus p plus pt to the power of n here. Okay, so in that case then, if we now apply this result here to this distribution, what we obtain here then for g of x in terms of t is we get, so I get bracket 1 minus p, so 1 minus 0.2 there, plus 0.2t, and that is all to the power then of n, where n in this case is 3. Okay, so we just simplify this here then, I get 0.8 plus 0.2t there. Okay, and that is to the power of 3 there. Okay, so nice and straightforward. That gives us the solution there to part A. Now for part B then, so what do we have here for part B? Well, we're told that two independent observations here, x1 and x2, are taken from the distribution of x here. The random variable y is defined as follows. So for part B then, it now asks us to find the probability generating function of y here. So before we even consider the PGF then of y, let's just consider the PGFs then of x1 and x2. And I actually promise you it's a lot more straightforward than it actually looks here, because for the PGF then of x1 here, so that's going to be g of x1 here in terms of t. Well, in this case, this is actually the same result as here, right? So that is 0.8 plus 0.2, so 0.2t there to the power of 3. And the same is true then for the second observation here of x2 and the PGF of that. So g of x2 here in terms of t, again, we just get this result here. So 0.8 plus 0.2t to the power of 3 here. Okay. So in that case then, if we want the PGF here, the probability generating function of y, which is the sum then of our independent observations here, x1 and x2, in that case then, the PGF here of y, so that's g of y in terms of t, that then is the product here of these two PGFs, right? That's just a basic property of probability generating functions. That's going to be g of x1 here in terms of t times by g of x2 in terms of t. Okay, so let's put all this together here then. So g of y in terms of t, what do I get here then? So g of x1 in terms of t, that's just this here. So I've got this here times by itself again. So really what I've actually got here is the square of 0.8 plus 0.2t all to the power of 3. So we've got the square of that, right? So let's put this in brackets here. So we've got 0.8 plus 0.2t. This is all to the power of 3 here. and then we square this full expression here. Okay, so now let's just apply basic properties here of indices. So we've got this power here raised to another power. We simply multiply the powers together then. So what I get then for g of y here, the PGF of y in terms of t then, is we get, so I get this result here to the power of 3 times by 2, which is 6, right? I get 0.8 plus 0.2t, like so. And this here then is the power of 3 times 2, like we said, that is 6 there. Okay. So there we have it. So that gives us the PGF there of y, and that gives us the solution to part B. Now for part C then, we're going to need a little bit more room here. So let me just quickly clear the screen then so we can have a go at part C. And as we can see here then, for part C, it asks us to use calculus to show that the expectation of y is equal to 1.2. And it also asks us to find the value of the variance of y here. So let's give part C a go here. Now we have just erased it, but what you will need is the probability generating function of y here from part B. Let me just jot that down again, just in case you don't have it to hand. So g of y in terms of t here, this is equal then to, so it's 0.8 plus 0.2t here to the power of 6, right? Now, as you can see then, the question does say, or this part of the question does say, use calculus. Now, you should be aware, if we want the mean here, the expectation, and the variance, we do need to differentiate our PGF then, okay? So I need to differentiate here g of y in terms of t. So I need g prime of y in terms of t. So g prime of y in terms of t. So this here is the first derivative then of our PGF for y here in terms of t. So to differentiate this here, hopefully nice and straightforward, we're simply using the chain rule then. So just some basic A-level maths differentiation here. So what am I going to get then? Well, we bring the power down in front, so I'm going to get 6. We then times it by the derivative here of the inside of the brackets, that would be 0.2. So 6 times 0.2, and I've got the bracket here, and don't forget we reduce the power by 1. So 0.8 plus 0.2t, and this here is to the power of 5. Okay. If we simplify this here, then 6 times 0.2, that gives me 1.2. I get 1.2 bracket 0.8 plus 0.2t there. And that is to the power of 5. Okay. So if we want the expectation of y here, so the expectation of y, you should be aware that the expectation of y is equal then to g prime of y when t equals 1. Okay, so that's g prime of y when t is equal to 1. So all I need to do here then is substitute t equals 1 into this expression here. I get 1.2 times 0.8 plus 0.2 times 1, so that's 0.2. And that is to the power then of 5 here. Okay, 0.8 plus 0.2 is 1. 1 to the power of 5 is 1. I've got 1.2 times 1, and that gives us 1.2 there. That's required, right? That's what it asks us to find here. So therefore, the expectation of y, e of y here, is equal to 1.2 as required. Okay, so that's the first part done, or the first half of part C. Then we now also need to find the value of the variance of y here. So to now find the variance here of the discrete random variable y, we now need the second derivative here. Okay, so we now need g prime prime of y in terms of t here. Okay, so what I now need to do here is differentiate then g prime of y, so that's this result here, this expression then, again in terms of t. So what am I going to get here? Again, just basic chain rule. So it's going to be 1.2 times by the power here. We get 1.2 times it by 5. And don't forget, we also times by the derivative then of the inside of this bracket here, which would be 0.2. So 0.2. And then we times by the bracket here, but don't forget, we also need to reduce the power by 1. So I get 0.8 plus 0.2t. Reduce the power by 1 here. So this is all to the power of 4. Okay. So if we now simplify this here, 1.2 times by 5, then times it by 0.2. What I actually get then is just 1.2 again here. So I get 1.2 bracket 0.8 plus 0.2t to the power of 4 here. Okay. So now to find the value of the variance here. So the variance of y here, this is equal then. So this is g prime prime of y when t equals 1 plus, so it's now plus g prime of y when t equals 1 minus then the square here of g prime of y when t equals 1. Okay, don't forget to square this bit here. Well, g prime prime of y when t equals 1. So if we evaluate that down here, so g prime prime of y when t equals 1, again, nice and straightforward here. It's going to be 0.8 plus 0.2 times 1. So that's going to be 1 to the power of 4. So 1 to the power of 4, again, is just 1 times by 1.2, and we get 1.2 again here. Okay, so I've got 1.2 plus 1.2. Don't forget we established that at the top here. So that was 1.2. And then we subtract here 1.2 squared. Okay, so let me just quickly do it on my calculator here just to make sure I do give you the correct answer. So 1.2 plus 1.2 and then minus 1.2 squared. And hopefully if you do that correct, then what you should find here is we get 0.96 there. Okay, so the variance of y here, so var y, that is equal to 0.96 there. Okay, and there we have it. So that gives us the solution there to question 2. And finally then, if we take a look now at the very last question here, question 3, where we have the probability generating function of the discrete and variable x here, which is given as follows. We can see the PGF here for x. So for the first part of this question, then part A, it asks us to show that k is equal to 1 over 64. So for part A then, how do we show that k is equal to 1 over 64? Well, we need to use the following property here for probability generating function. So we're going to use here, so use the fact that g of x, so g of x here, when t equals 1, is equal to 1, right? So in that case then, for us here using this PGF then, g of x when t equals 1, that is equal then to k times 1 plus 4 lots of 1, so that's going to be 4, plus 3 lots of 1 squared, so that's going to be plus 3. We then square that here, and this is equal to 1. Okay, just a basic property here of probability generating functions. So now then, if we square this here, so 1 plus 4 is 5, plus the 3 gives us 8. So 8 squared is 64. So we get 64k is equal to 1. Divide both sides by 64 then, and we get that k is equal to 1 over 64. Okay, and there we have it. So that is the solution to part A. Hopefully nice and straightforward there just to get us started. Now for part B then. So for part B here, it asks us to find the probability that our random variable x here is greater than or equal to 2. So to do part B here, what we actually need to do is expand this bracket here. So this bracket is squared, right? So to evaluate this probability here, as we mentioned then, we need to find the full expansion here. So let's just find the expansion then of this bracket here squared. So 1 plus 4t plus 3t squared. That's all squared then. So in that case, that is simply 1 plus 4t plus 3t squared. And we times it by itself again. So 1 plus 4t plus 3t squared. Like so. So now if we expand these double brackets here, I've got 1 times 1, so that's 1. 1 times 4t, so that's plus 4t. And finally 1 times 3t squared, we get 3t squared there. Okay, let's keep going. I've now got 4t times 1, so that's plus 4t. We then have 4t times 4t, so I get 16t squared. And then finally 4t times 3t squared, I get 12t cubed then. So 12t cubed. And then finally, the final three terms here. So I've got 3t squared times 1. So plus 3t squared. We've got 3t squared times 4t. So I get 12t cubed again. And then finally here, 3t squared times 3t squared. I get 9t to the power of 4. Okay. So if we collect like terms here and just basically simplify this full expression, then what would I get here? So I'll just give you the simplified form. We get 1 plus 8t. So 1 plus 8t plus 22t squared. So plus 22t squared plus 24t to the power of 3, or 24t cubed. And then finally here, plus 9t to the power of 4. Okay. So clearly then for this PGF here, don't forget we need to times it by k. So what I've basically done here is find this expansion. I just now need to times it by k. So in that case then, g of x here, in terms of t, that is equal to 1 over 64. So 1 over 64 times this expansion here. So 1 plus 8t plus 22t squared plus 24t cubed plus 9t to the power of 4. Okay, like so. Now we want the probability that x is greater than 2, or greater than or equal to 2, I should say. So the probability that x is greater than or equal to 2, like so. Then this would correspond then to the powers here of 2 or greater. So 2, 3, and 4 here. So what I now need then is the respective coefficients here. So don't forget we do times these through by 1 over 64. So what I've got then, so I've got 22 plus 24 plus 9. 22 plus 24 plus 9. But we've times each one of these by 1 over 64. So this is all over then 64 here. So 22 plus 24 plus 9 over 64. This gives us then 55 here over 64. Okay. So there we have it. So that's the solution to part B. And then finally here, let's just box this off down here. So for part C then, it asks us to write down a probability generating function for y is equal to 3x plus 1. So for y equals 3x plus 1 here. Okay, so y equals 3x plus 1. Hopefully you recognize that we need to use the following result here. So we're going to use g of y then, the PGF for y here, in terms of t. And that is equal then to t to the power of b times by the PGF then for x here. So g of x in terms of t to the power of a. Okay. So the only question left here then is what is a and what is b? Well, this is ax plus b. Okay, so this is for y is equal to ax plus b. Okay, so in that case then, a here is this coefficient, which is 3, and then b is this term here of 1. Okay, so if we now put all this together here then for the PGF for y, so in that case then, g of y here in terms of t, what do we get then? We get t to the power of b, so that's t to the power of 1. So we get t. We then times this here by the PGF for x in terms of t to the power of a. So I get t to the power of 1. I will put the power of 1 here just to illustrate that it corresponds to b equals 1. We then times it by 1 over 64, because that is my PGF for x here. So what do we have then for the PGF for x here? I've got 1 plus 4t plus 3t squared, all squared. Now basically, wherever I see a t here, replace it with t to the power of a. So that's going to be t to the power of 3. So we get 1 plus 4 lots of t cubed. And then finally, we have 3 lots of t cubed, which is then squared. So 3 lots of t cubed squared. And this full expression then is squared. Okay, so I'm going to room a little bit here. Hopefully you can still what I've got, or hopefully you can still see what I've got here. So I've got 1 plus 4 lots of t cubed plus 3 lots of t cubed, which is then squared because I've got 3t squared. And this full bracket here is then squared. So let's simplify here. So what do we have then? Well, I've got t over 64. So t over 64. Then we times this here by 1 plus 4t cubed. So 4t cubed there. We've then got 3t, so 3 to the power of 2 then. Oh, sorry, let's try that again. This 3 here, this power, is then raised to another power of 2 here. So don't forget when we've got a power raised to another power, we multiply those together. So I get t to the power of 6. I get 3t to the power of 6. Like so. And then this full bracket here is squared. Okay, now obviously, we don't need to, find the expansion here. It just asks for a probability generating function. So don't overcomplicate things. Don't make life harder than it needs to be. We're already doing quite challenging maths here. So there we have it. That gives our solution. So that is the PGF then for y equals 3x plus 1. And there we have it. So that gives us the solution there to the very last question, question 3. And that actually brings us to the end then of this video here on exam revision for probability generating functions.